Hi, this is Kevin Buzzard, and I'm going to go through sheet 4 of section 6 of my Formalising Mathematics 2022 course. I'm basically going to speed run it because this is sort of harder stuff, and I don't know, I mean maybe it's not harder stuff. The idea is we're going to construct the integers. If you've constructed the naturals, e.g. via Peano's axioms, you can construct the integers by putting an equivalence relation on naturals squared. AB is equivalent to CD. If the idea is that you want to represent the integer z as a minus b, and so these should be equivalent if a minus b equals c minus d, but that doesn't make the problem is the difference of two naturals might not be a natural, and so you have to rewrite it as a plus d is b plus c. And if you think about it a little bit, if you imagine the natural squared as the sort of top right quadrant of a plane, then the equivalence classes are diagonal lines, and somehow there's a diagonal, and now you can imagine mapping that onto a sort of a diagonal copy of the integers. Let's just get on. So before we start, we need to work out how to steer products, naturals cross naturals. So the constructor is these round brackets here, and if foo is the ordered pair 3753, then the way you get the two parts from it, you can use foo.1 and foo.2. Those are definitionally the first and second parts. And the other thing you need to know about is if you have a pair, if A is type natural cross natural, then A is clearly encoding a pair of naturals, and you can get to them with cases. There you see x comma y dot first is the same as x comma y dot 1. It's definitionally x, and this is definitionally y, so this is true by Raffel. So here's the definition of our binary relation on nat cross nat, and you see a general element of nat cross nat. I'm calling it AB, right? So it's a pair A comma B, but I'm just giving it a name AB, and CD, and so AB.1 I'm thinking of as A, and AB.2 I'm thinking of as B. So this just says A plus D is B plus C. And so this will be true by Raffel because it's definitional. And similarly here, I mean if I rewrite RDEF so you can see what's going on, oh hard luck. It's difficult. I mean the problem is it's also true by Raffel because pair brackets A comma B dot 1 is equal to A again definitionally. So those are our definitions. I'm not sure I'll be using them because I'm going to be taking everything apart with our cases. So let's prove our relation is reflexive. So rintro AB. It's just instead of just intro x and then cases x. If I rewrite R, let's see what this. See what the thing says. What are we trying to prove? And then desimp it. So we're trying to prove that A plus B is B plus A. So in fact, this, I mean, so we could just ring, right? That's, I mean, that would be the way to do it. I guess it's called, I could exact add com. I could probably do it like that. Yeah, that works as well. And if you do it like that, then you could just do it like that. So symmetric, rintro, I guess A, B, C, D, and then there'll be some H. So let's rewrite RDEF primed at everywhere, and then what somehow made this thing feasible was I realised that Linarith solves this. I was in the previous sheet. You see, look at that. In the previous sheet, I was like, yeah, well, now we've got to sort of rewrite. What have we got to do? You see, we've got B plus C, but this is C. Let's rewrite add com. This is what I was doing in the previous video, and now this is a B plus C, so we can rewrite H that way, and now finally, we can ring it there. But the Linarith tactic just nails this completely, which basically is what makes this sheet feasible. So transitivity, what have we got here? We've got AB, CD, EF, so, and then H1 and H2, I guess, and then rewrite RDEF primed everywhere. And then again, Linarith will do this one. I hope. Yes, it does. So we've proved that R is reflexive, symmetric, and transitive. So now we can make this settoid instance. The settoid packages up the binary relation and the three proofs all into one object. we make it an instance, and now we get this notation, this equivalence notation, which now Lean will somehow use automatically. But again, this is true by definition, I would imagine. Yeah. So there we go. So now we'll define my int to be the quotient. So these are what I claim is the integers, and now let's prove that they're a commutative ring. So we start by defining 0. It's the equivalence class of 0, 0. So the proof of that will be REFL. Now let's define negation. So the way negation works. So remember the idea is that this pair AB is supposed to represent the integer a minus b, and so b minus a, its negation is represented by ba. So this is, you see, that's the map that we want to descend. We want to descend a map on naturals squared, sending a comma b to b comma a. So I'll take an arbitrary ab input, and then I'll replace it with ab.2, ab.1. And now we've got to prove that that descends to a map on the quotient. So this is one of these goals that looks terrifying. Let's see what we've got to do. Let's start with that. And we need another one. So we've got two elements of n squared, and we're assuming they're related. And then, so that's the goal, basically. We've got to prove that if two naturals are related, then when we flip them, the flips are also related. So that's what we're trying to do. And I guess we can rewrite our def primed everywhere. That has failed, which is a bit annoying. I see. So now, this is if it's not R now, it's equiv. And rewrite works up to syntactic equality. So now we have to rewrite equiv def everywhere. There, has that worked? Yes, and now Linarith should do this. A bit of a bonus, really, that Linarith does that. I don't think it's quite what it was designed to do, but it seems to work anyway. So that's now, we've now got a negation on the integers, and that will be REFL, because that was how it was defined at the top. It's and now what? Now addition, and so you just add the components, right? A comma b add c comma d is ac plus bd. And again, we're going to have to prove that that's well defined. So it's going to be rintro ab cd. How are we doing? And then this is h, and now e f. Oh, we can't have h's. We'll have to have h1. And then GH, and then it's going to be H2. And now what does the goal say? Right, and now we've got equivs everywhere, so let's rewrite equiv def everywhere. And again, Linarith should do this. Somehow I wasn't expecting this. I've known this before, but I haven't really internalized it. And add def, that's just the definition of addition, so that should be REFL. And now we've got to prove, so now you see we've got addition, 0 and negation, and we've been training the simplifier as well secretly. These lemmas are tagged simp, so the simplifier should be of some use to us. So now how are we going to prove add a sock? So the routine here is you do intros, x, y, z, and now you see these aren't, there's no naturals around, there's no pair of naturals around, so we need to do quotient induction. Quotient dot induction on 3, because there's 3 variables, x, y, and z. Let's try applying it. That's worked, and now we don't need them anymore. So now we've got questions about naturals cross naturals. So now this is going to be rintro. Let's see what it says. A, B, C, D. We need 3 of them, I guess, for associativity. E, F, and now let's see how far the simplifier gets. So yeah, I guess ring will do this now. There we go. 0 add, so now that's the same, that's intro x, and then apply quotient induction on just one of them this time, x, clear x. And now rintro AB, and now And now let's see how far simp gets. Simp doesn't do it. But if we tell simp to use add com as well, simp will do it. So there we go. We didn't need ring. And add 0. I bet the proof. Let's see if the same proof works. There you go. It has worked. Did we need the add com? Yes, we do. It's so there you go. Add 0 and 0 add both boil down for integers. Both boil down to add com for the naturals. Add left neg. So again, add left neg. That's just a theorem about one variable. That's the fact that if you add x add negative x is 0, right? Let's see. Yeah, it's negative. Sorry, it's negative x add x is 0. Did it work? It did work. Did the simplifier do this one? Oh, look at that. That boils down to commutativity of addition as well. So all these axioms for the integers somehow all boil down to commutativity of addition. Commutativity of addition on the naturals. So I would imagine that, let's try this. Is what you would have thought that commutativity of the addition on the integers would boil down to. That's because this is wrong. We need to do addcom is addcom's got 2 variables, so this is on 2 x y clear x y, and then we need to intro a b c d. Now let's see. There you go. That one's worked. So what did it boil down to? It boiled down. Oh wow! It boiled down to something quite complicated. In fact, I'm quite surprised that simp addcom does that. But apparently it does, so let's not complain. And that's the proof that the integers are an additive group, a commutative group under addition. So here's the definition of 1. It could be 1, 0. We could have used anything. We could have used 4, 3 or whatever. 0, 1, 0 is somehow the simplest thing we could have used. So this will be REFL. And multiplication. So I did it by hand, right? A minus B times C minus D is you multiply it out, and then you collect it up into the things which you've got a plus and the things which you've got a minus. And so it's like sort of the complex numbers. There's a real part and imaginary part. Here we're doing the integers. We've got a sort of positive part and a negative part. So this is the positive part, and this is the negative part. Unless I made a mistake. If I've made a mistake, well, we'll find out pretty soon if I've made a mistake, because this proof won't work. And so now let's look at the definition of add. Let's try this. And I suspect it won't work because multiplication is not linear, but it's a good start at least. So let's see what the goal is. So this is a bit of a nightmare. If we had to do this from first principles, this would be horrible, right? Ring isn't going to do it because it relies on H1 and H2. But in rehearsals, nlinearith did it. And indeed, nlinearith has done it again. That's a relief. Actually, I'll tell you the truth. In rehearsals, nlinearith didn't do it because I put a 1 here. And I was kind of horrified. I was like, oh no, nlinearith has failed. I'm going to have to solve this by hand. And then I discovered that, in fact, it was because of a typo. I noticed the typo because there's an asymmetry. 1, 1, 2, 2, 1, 2, 1, 1. That doesn't sound right, does it? It's 1, 2, 2, 1. So anyway, that's the proof that that's a definition of multiplication on the integers, and a proof that it's well defined. And so this will be REFL again. Now finally, last thing left to prove is a commutative ring. So mollesoc, I mean, where's the proof of addersoc? It's going to be very similar to the... I suspect that just might be the same proof. Mollesoc goes there. Yeah, to simp do it. So simp leaves us with that mess, and then ring finishes it. And 1 mul, that's got 1 variable, so let's try this one. I wonder if addcom will do it for us. Yeah, it did. I wonder, does simp do it? Yes. Every single one, like, there you go. Did you know that? The proof that multiplication by 1, the proof that 1 is a multiplicative identity on the integers, defined as this quotient, boils down to commutativity of addition. Oh, I see. It somehow it doesn't. I see. I'm somehow lying. I mean, maybe I'm not lying. It boils down to commutative addition anyway, and this will be the same, right? I guess the simplifier might be doing other things as well. I'm suddenly. This might not be. I mean, it boils down to commutative addition plus things that the simplifier. The simplifier doesn't know add com, right? The simplifier knows things like a plus b minus b is a. The simplifier knows things where the left-hand side is more complicated than the right-hand side, and the problem with add com is that doesn't apply. What's left distrib? That's got 3 variables. So let's try mull a sock because that had 3 variables as well. Boom. That has worked. What did simp? There you go. Simp brought it down to that, and then ring finished it. Right distrib will be the same thing. Oops. Right distrib will be this. There, does that work? Yep. And mulcom, I'll use addcom because there's 2 variables. There we go. Boom, boom, boom. Does that work? Oh no. Oh, that's okay. So let's just do simp ring. Goals accomplished. There you go. No warnings, no errors. Integers with commutative ring. I mean, you know, now you can do what you like. You know, we could just make. We could make, I don't know, we could define the coercion. Let's just do it in here. Define the coercion from the naturals to my int. My int. How would that? I guess we could do. Let's let a be a natural. Let's define my int. And what was the map? So what's the map? What's the natural map from the naturals to the integers? This wasn't done in rehearsal at all, by the way. So this could all go horribly wrong. And it's going to be that. So now we've got the map, and we could prove. You know, I don't know. We could prove it's an additive group homomorphism. I guess we could. Oh, I suppose these aren't groups. We could prove it's an additive monoid homomorphism. We could do def lemma coe 0 coe 0 equals 0, and that's probably refl. Yeah. And lemma coe add, so this would have a and b naturals. I claim that coe of a add b is going to be coe a. Coe stands for coercion. Coe a plus coe b. Begin end. If we're lucky, this is refl. It's refl, isn't that great? I bet coe mull won't be though. Let's try coe mull. Let's do coe 1 might be. Coe 1. Oh, let's copy this one. Coe 1 says that coe 1 of 1. Yeah. That's just term mode. I mean, that's begin refl end. And then coe mull. I suspect this won't be refl, so we might have to do some work here. Coe of a times b is coe of a times coe of b. Yeah, refl didn't work. So now we're going to have to do some work. I guess we could do unfold coe, and then we could try simp, and we're done. So there we go. So we could probably do simp coe. Is that a thing? Excellent. So there you go, and you can just keep going. You know, you define prime numbers. You can do whatever you like. You know, you can just make mathematics. It's completely, I don't know. I think it's great. Thanks for watching.